All right, logs and application of exponential logarithms. So you can read through this about earthquakes, but the Richter scale uses logarithmics to deal with what a magnitude of earthquake becomes. A couple things on here to notice. On the chart at the side, the highest magnitude earthquake was 9.5 in Chile, the Richter scale reading, and then they've got all sorts of different measurements off to the right. Any earthquake having magnitudes in excess of 6 are considered dangerous. All right. Note that every scale is 10 times as intense as a zero reference. All right, so these are all powers of 10. So an earthquake with a magnitude of 2 is 10 squared times as intense as the zero reference point. So let's complete the following. An earthquake of magnitude 8 is how many times as intense as an earthquake of magnitude 7? So they're one notch away on that chart on the right. So that would be 10 times as intense as an earthquake of magnitude 7. Earthquake magnitude 7 is how many times as intense as an earthquake of magnitude 3? Well, there are 4 levels apart on that scale, so that would be 10 to the exponent 4 times as intense. Or you could write that as a number if you wanted. Earthquake of magnitude 4 is how many times as intense as a magnitude 6? Well, again, there are 2 spots away on that chart, so it's going to be 10, but now it's less than, so 10 to the negative 2 times as intense. An earthquake of magnitude 4.8 is how many times as intense as an earthquake of magnitude 6.8? Again, 10 to the negative 2. In 1960, the earthquake in Chile had a Richter scale reading of 9.5. Was how many times as intense as the 1976 earthquake in Italy, which had a reading of 6.5. So that should be 10 to the exponent 3 times as intense. The 1983 earthquake in Colombia had a Richter scale reading of 5.5. So the Chilean earthquake was, oh, this should have been 10 cubed, sorry. The Chilean earthquake was 10 to the 4th times as intense as the earthquake in Colombia. And finally, F. 66 earthquake in Turkey had a scale reading of 6.9, and the one in Japan in 33 had a rating of 8.9. So that is 10 to the exponent negative 2 times as intense. All right. So if we're going to compare earthquake intensities, that's the next page. We've seen how to compare intensities of earthquakes whose magnitudes differ by an integer. How would we compare the intensities of the 60 earthquake in Chile, which was 9.5, and the 05 earthquake in Chile, which had a magnitude of 7.8? So to compare these magnitudes, consider the following. The magnitude of an earthquake is given by this formula. M equals the log of I over IO, where I is the earthquake intensity and IO is the reference intensity. So they'll always define the variables for you. So the intensity of earthquake 1 would be M1, intensity of magnitude of earthquake 2 would be M2. We can use the law of logs to show that magnitude 1 minus magnitude 2 should equal the log of intensity 1 divided by intensity 2. So the laws of logs, which we already know. Magnitude 1 was the log of intensity 1 over intensity O. Magnitude 2 is intensity 2 over intensity O. Take the log of that one. If we're dividing within a logarithm, we can write it as a subtraction, right? So log intensity 1 minus log intensity O. subtract log intensity 2 minus log intensity O. And now what can we do? Expand out this bracket. So you got log intensity 1 minus log intensity O minus log intensity 2. And the negative times the negative makes us plus log intensity O. And so negative log intensity 0 plus positive log intensity O, they're going to become extinct. And we're left with log intensity 1 minus log intensity 2. Now if I want to write that as a single logarithm, log of intensity 1 over intensity 2. Back to a single logarithm, we can write that subtraction of two logs with the same base as a single log. So we've proven this formula. All right. The result, intensity 1 divided by intensity 2 is going to equal 10 to the exponent magnitude 1 minus magnitude 2. Where does this come from? How can we come up with that formula from the one that's above it? This is a logarithmic equation. This is an exponential equation. We're changing logarithmic to exponential form. The base of the common log is 10. So 10 to the exponent m1 minus m2 should equal log intensity 1 divided by log intensity 2. So all we're doing is changing form from log form to exponential form. These are the same equations, just in two different forms, right? So we've been doing this the whole time on the last thing, right? As long as these were integers, we just said they're 10 to the exponent 3 times more intense, or 10 to the exponent negative 4 times less intense, right? Well, now it's true, but they don't have to be integers. So we can use this formula for any kind of intensities. So how many more times intense was the 60 earthquake than the 2005 earthquake in Chile? Well, use this. Intensity 1 over intensity 2 would be 10 to the exponent. Magnitude 1 was 9.5 minus magnitude 2 is 7.8. So 10 to the exponent, 9.5 minus 7.8 is a whole 1.7. And then use your calculator. If you go 10 to the exponent 1.7, what do we get? $50 times more intense. All right. So either answer here would work. 10 to the 1.7 times more intense, or that's a relatively small number, so you could figure that one out. Example 3. Major earthquake of magnitude 7.5 is 375 times as intense as a minor earthquake. Is the magnitude of the minor earthquake greater or smaller than 7.5? What do you guys think? If this earthquake is 375 times as intense as this earthquake, would the magnitude of the minor earthquake be greater or smaller than the magnitude of 7.5? Smaller. It's got to be smaller, right? This one's more intense by a number greater than 1, so the minor earthquake could have a smaller intensity. Use this formula then, or smaller magnitude, sorry. Use this formula to determine to 1 decimal the magnitude of the minor earthquake. So we know the comparison of the intensities is 375. And that should equal 10 to the exponent. We know what magnitude 1 is, 7.5. We don't know what magnitude 2 is. So you have to solve that equation. How do we do that? If we can't write 375 as a power of base 10, we learn to take the common log of both sides. Or you can take the natural log. But I can take the common log because the power of that base, that exponent is 10. Base of that exponent is 10. So the common log of 375 should equal the common log of 10 to the exponent 7.5 minus magnitude 2. We know we bring this exponent down in front on the right side of this equation. So we get 7.5 minus magnitude 2 times the log of 10. And the value for the log of 10 is 1. The common log of 10 is 1. So you've got the log of 375 equals 7.5 minus magnitude 2. So if I want to solve for magnitude 2, I could bring to this side of the equation, and I could minus the log of 375 from both sides. And that's calculator work. So 7.5 minus the log of 375 is 4.925 and so on. Determine one decimal place the magnitude. So the magnitude is 4.9. All right. So we're going to have to maybe use this formula. Loudness of sound. Loudness of sound is really measured in bells, named after Alexander Graham Bell. The current unit used is the decibel, which is equal to 1/10 of a bell, but decibel is the most common one. The Bell scale, like the Richter scale, is a logarithmic difference of 1 bell, or 10 decibels, right? Corresponds to a factor of 10 difference in sound intensity. So a leaf rustling is 10 decibels, or 1 bell, and it's 10 times as intense as the threshold of hearing. So again, everything's based on a scale of 10. A whisper, which is 30 decibels, is 10 cubed, or 1,000 times as intense as a threshold of hearing. And it would be 10 squared, or 100 times as intense as a leaf rustling. And you've got the decibel scale over to the right. All right. So a jet engine is roughly 130, 35, 40, about 140 decibels when you're 20 meters away. Threshold of pain is 125 decibels. Rock concerts, 120. All right, and so on. Complete the following using the chart above and to the right. A power saw is 120 decibels. How many times as intense is that as a telephone dial tone, which is 80 decibels? So, I mean, if we went to bells, this is 12 bells, and this is 8 bells. And we would say they're 10 to the exponent. They're 4 bells apart, so 10 to the 4th. All right. Jet engine at 20 meters, 145 decibels, and threshold of pain is 125. So again, this is 14.5 bells, and this is 12.5 bells. So how many times 10 are they apart? 10 to the exponent 2. They're 2 integers apart, so it would be 10 squared times as intense. And a whisper is how many times as intense as conversation? Again, if you went to bells, 3 to 6, this one would be smaller, so 10 to the negative 3 times as intense as conversation. So again, decibels are based on sound and a power of 10 scale. Sound intensities, if we're going to compare those, we've seen how to compare the intensity of sound whose bell levels differ by an integer, but again, what if they don't? Just like with our magnitude readings. Loudness of sound can be measured in decibels or bells. The intensity of 2 sounds can be compared using the formulas where I represents sound intensity and IO represents the reference sound intensity or the threshold of hearing. So again, just like Richter scale reading, bells equals common log of intensity over intensity reference, or if you want to do decibels, it's 10 times that. All right. So you could use either of these formulas to compare intensities. This one's just being divided by 10 as the exponent. All right. So same as we did with the Richter scale reading, we could derive those formulas, or we could just use them. Example 5, how many times more intense is the sound of a piano playing than a whisper? So again, if you're going to compare those intensities, intensity of a piano playing, so that's intensity 1 over intensity of a whisper, intensity 2. They're talking about decibels. We could change those into bells if you prefer, and we don't have to worry about dividing by 10. You do it automatically. So that's 10 to the exponent. Intensity 1 is 6.7 decibels. Sorry, 6.7 bells. Intensity 2 is 2.2 bells. So 10 to the 6.7 minus 2.2. 10 to the 4.5. Example 6. Given that formula, show that the decibel level for the threshold of pain has a sound intensity of 10 to the 12.5 times the threshold of hearing, I-O. All right. So we're told the decibel level of pain. We're going to put that in where the decibel level falls. So 125 is going to equal 10 times the log of intensity over intensity O. Divide both sides by 10, and you get 12.5 equals the log of intensity over that threshold of hearing intensity. Now what can we do? This is an exponential form, so let's change the logarithmic form to exponential form. Common log has a power of, or has a base of 10, so let's change this into a power of base of 10. 10 to the 12.5 would equal I over I-O. And they should show that this level of threshold has an intensity of 10 to the 12.5 times I-O. So I want to solve for this I, this intensity. So I multiply both sides by I-O. So 10 to the 12.5 times that threshold of hearing is the intensity of threshold of pain. So we've proven that. All right. The last one to look at, I believe, is pH scales. And if you guys have done your chemistry, you've dealt with these already. So let's have a look at the pH scales. 09, Soren Sorensen, a Dutch chemist, introduced the term pH representing the expression the power of hydrogen to measure the extremely wide range of hydrogen ion concentration in substances. pH scale measures the range of hydrogen ion concentration by determining the acidity or alkalinity of a solution. pH levels below 7 represent increased acidity and above 7 represent increased alkalinity. The value 7 represents the neutral level of pH scale, where the solution is neither acidic nor alkaline. So 7 is the neutral solution as a pH level. Similar to the Richter scale reading, the pH scale is logarithmic. A difference in 1 unit of pH corresponds to a factor of 10 difference in intensity. This means that each whole number step represents a 10-fold change in intensity. Therefore, vinegar has a pH of 3. It is 10 times as acidic as tomato juice, which has a pH of 4, 100 times as acidic as normal rain, which has a pH of 5. On the other hand, household ammonia, pH of 11.5, is 10 times as alkaline as milk of magnesia and 1,000 times as alkaline as seawater. That's all based on this horizontal scale up above. All right. So again, complete the following. Use the approximate pH values given. We've done 2 of these. I want you to try and do this one on your own. Then I'll go over it. So tomato juice is how many times as acidic as pure water? Here's tomato juice. That's more acidic than pure water, right? More acidic. So if it's more acidic, it's got to be a greater amount. Well, there's a difference of 3 from 7 to 4 on this scale. So that's 10 cubed times as acidic, or you could write 1,000 times as acidic as pure water. Eggs are how many times as alkaline as pure water? So eggs are more alkaline than water is by a step of 1 on the scale, 7 to 8. So they're 10 to the first, or 10 times as alkaline as pure water. But eggs are how many times as acidic as pure water? Well, now we're going the other direction. Eggs are not as acidic as pure water. Pure water is more acidic than eggs are, right? So we would say eggs are 10 to the negative 1, or 1/10 times as acidic as pure water. So make sure we know which way we're going on this scale. More acidic, more alkaline. Milk of magnesia is 1,000 times as alkaline or as acidic as blood. Well, here's milk of magnesia. There's blood. This is greater. So milk of magnesia is more alkaline. It's further down the alkaline scale, so it's 1,000 times as alkaline as blood. What's 100 times as acidic as normal rain? Well, here's normal rain. More acidic than that, 100 times would have to be going in this direction. So 2 levels up should be vinegar. So vinegar is 100 times more acidic than normal rain, and eggs are 1 over 10,000, or you could say 10 to the negative 4 times as alkaline as what? So here are eggs. They're not as alkaline as the thing that we're comparing it to. 10 to the negative 4, so that would be washing soda. Washing soda has a higher alkalinity. Eggs have a smaller alkalinity than washing soda. All right. Page 316 then. Let's compare acidity and alkalinity of solutions. Again, to find out how much more acidic or alkaline one solution is, we can use this comparison. 10 to the pH of 1 minus the pH of the second. Pure water, swimming pool water, and seawater have pH levels as given. Seawater is how many times as alkaline as pure water? So again, use our base of 10. Seawater has a level of what? 8.4. Seawater is the third one. So 8.4 as alkaline. And the level of pure water was 7. So 10 to the 1.4 times as alkaline as pure water. Seawater is how many times as alkaline as swimming pool water? Again, 10 to the 8.4. Swimming pool water is 7.5. So 10 to the 0.9. All right. The pH of a solution is defined as the negative log of H positive, where H positive is the hydrogen ion concentration expressed in moles per liter. I think you guys used that one in chemistry, didn't you? Yeah. I hope so. Or you missed a lot. A patient gave a urine sample which was found to have a pH level of 5.7. What was the hydrogen ion concentration? Answer in scientific notation to 1 decimal place. So we're told the pH level is 5.7. So plug that into our formula where we see pH. That equals the negative log of H positive. All right. And we're looking for H positive. So get rid of that negative sign. So I've got negative 5.7 equals the log of H positive. And I can't really figure out this without putting it into exponential form. So common log has a base of 10, so the base of our power is 10. 10 to the negative 5.7 will equal H positive. Let's figure out that on our calculators. 10 to the exponent negative 5.7 gives us that number. Answer in scientific notation using 1 decimal place. So if I want to put that in scientific notation to 1 decimal place, that would be 2.0 times 10 to the negative 6. All right, is H positive, and that's in moles per liter. Example 10. Determine the pH of a solution to the nearest tenth if the hydrogen ion concentration is 3.4 times 10 to the negative 4. So now we're looking for the pH level, and we're given the moles per liter, H positive. So that is 3.4 times 10 to the negative 4. Well, that's purely calculator work. You can type that exactly as it is into our calculators. So negative log of 3.4, and the button that is scientific notation is second function above our comma. All right. So that's what it should look like. So it wants it to the nearest tenth, so our pH level should be 3.5. Okay. Great. That's that unit. You guys have your assignment questions? Away you go.